What's going on, everybody? It's Mr. Diamond, and today we're going to be doing the first two example problems from section 4.2. These are the two that do not relate to roller coasters. These are the other types of example problems. The first one being a car and the second one being a bucket. So our first example is the Vmax, or the maximum speed that a 1,025 kilogram car can safely take a 180-degree turn is 11.5 meters per second. If the path were a full circle, the radius would be, sorry, I'll keep this down so you can see a little better, hopefully, would be 30 meters. What is the force of friction, and what is the coefficient of kinetic friction? So now we're actually talking about our kinetic friction coefficient, which means we're going to be involving some of our equations in our force diagrams from earlier. As always, though, you want to start by drawing a picture. It doesn't have to be super fancy, but I'm going to go ahead and draw a square, and that's going to be my car. It's a great car. I'm very happy about it. And then we're going to say it's going to take its 180-degree turn. I know that's not really a circle, but it's going to, just for space concerns, that's my circle. And we know that if we were to expand this into a full circle, where this side is much more reasonably spaced, it would have a radius of 30 meters. We know that it's traveling this direction. I'm going to make it go that direction at least, 11.5 meters per second. And we know its mass is 1025. Okay, the first question is just asking for force of friction. So first thing we have to think of is we now care about where friction is. Where would friction be acting? Well, friction is going to be acting on the car when it's sideways, for example. So as it's actually like going, there is going to be friction pulling it backwards, and there's going to be the speed going forward. And then there's going to be kind of gravity and the normal force acting on it. But this isn't the friction we're really concerned about. We're more concerned with what is the friction that's allowing the car to make that turn. Because as we start turning it, this friction is no longer going to be pointing backwards. It's actually going to point, it's going to be centripetal, and it's going to point towards the middle of that circle. So to calculate what our force of friction is going to be, as it shifts from being pointing directly back to pointing towards the middle, we would expect it to be equal to the centripetal acceleration. That's the only thing there. So because only force in that direction is friction, we can say that force of friction is equal to sum of the forces, which is equal to ma. We know it's the only force that's acting on it to carry it around there if it's going at a constant speed, so we know that it must be equal to ma. And again, the reason we know that is because there are no other forces that are going to be acting on this except for this one. This is the only force acting inward. This is constant. This is the direction our acceleration points. That means that's the direction that our force is going. So looking at the information that we're given, we don't have our a yet, but we can solve for a. Acceleration is equal to v squared over r, and v in this case is 11.5. So 11.5 squared over radius is 30. We'll go ahead and plug that in. 11.5 squared over 30. I get 4.408, blah, blah, blah. We'll go ahead and do 4.408, blah, blah, blah. And that's meters per second squared. So if that's the acceleration the car is experiencing, the only way that acceleration can happen is if a force is acting on it. And the only force that could be acting on it is friction. So that acceleration is tied to the frictional force, which means force of friction is equal to ma. And if our a is this 4.408, we already know our m. Our m up here was 1025 kilograms times 4.408 blah, blah, blah meters per second squared. Kilogram meters over second squareds would give us newtons. We would get, we'll multiply that by 1025. 4518.54, blah, blah, blah. So we'll go ahead and do 4518.5, blah, blah, blah. We'll stop there. And that would be newtons. So because that frictional force is the only force acting in that direction, that force must be the force that is causing the centripetal acceleration, which means it must be equal to the centripetal force, which means it's equal to our value that we just calculated right here. So force of friction, if we round it to 3 sig figs, would be 4,520 newtons. All right, cool. But now we're running into a slightly different problem. We want to know mu k, and in case you forgot, we actually do already have one other problem. We already know that we can calculate force of friction because it is equal to coefficient of kinetic friction times the normal force. That's an equation that we got pretty familiar with back in that chapter. We couldn't have used it in the first part. I guess I probably should have brought it up because it would have been on your paper and you would have gone, oh, there's force of friction. But we don't have either of these pieces, so it wouldn't have really helped us. But now we have force of friction. And I said we didn't have this, but we can solve for the normal force. If we remember, this is the normal force, the one that's pointing up. The force of gravity is here. And this is our velocity in my little diagram that I drew here. Because they're the only forces acting in that direction, the car is not lifting off, the car is not tilted in any way. Again, that's where the banked curve stuff comes in that I'm not really feeling. We can say that Fn must be equal to Fg, and Fg is equal to mg. They're just going to be pointing opposite directions. So where Fg is pointing down, Fn will be pointing up. It'll be positive. So now we can actually set our equation, mu k is equal to the force of friction divided by the normal force. And our force of friction is our 4,518 blah, 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 divided by, to get our normal force, we just need mg. M is 1025. Gravity is 9.8. Again, we want it to be positive because the normal force is going upwards. So I'm going to take my 4,518 blah, blah, blah that I had saved from right here. I'm going to divide that by 1025 times 9.8. And I will get that the coefficient of friction is equal to 0.4498 blah, 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 or 0.450. Remember, coefficients of friction don't actually have any units associated with them. They're just a coefficient. They're a constant that's used. Also, remember that most of our coefficients of friction were decimal numbers. They were like below 1, kind of between 0 and 1 were the values we were normally looking at. So this number actually makes sense. It is a reasonable coefficient of friction for the car to have, for there to be between the road and the tires. So that gets us through our first problem. And again, I know it may be a little bit tough to figure out, like, well, why did we know this worked? Why did we know that was the only force? And it's because if you think about the car going, as the friction is no longer pointing backwards, it's got to be pointing in there because something has to be pointing inwards, has to be providing that centripetal acceleration, has to be allowing our velocity vector to change their positions. And if those things exist and there's nothing else there, the car isn't on a rope or on a string or anything like that, we know the only thing that could be providing it would be the friction. The friction of the tires is what's allowing it to go around that turn. So it's the only force going that direction, which means it is exactly equal to our ma, our mass times acceleration, because it's the only thing that's involved in the acceleration process. Okay, for example number 2, we're going to get a little bit weirder. We're going to take a bucket. So I'm going to draw my picture up here. I'm going to draw my point that's going to be my center of my circle. And then we're going to be swinging this bucket around at a bunch of different points. So I'm going to get my picture, and then I'm going to draw some arrows to kind of help us visualize it. So we have a bucket that's spinning in a circle, but this time it's a vertical circle. It is not a horizontal circle. So here, this was going in a horizontal circle, which meant that, like, the normal force and gravity weren't really affecting anything. But now that it's a vertical circle, gravity is actually going to have to be involved. We're going to have to consider gravity in our calculation. And the question states that the mass of the bucket is equal to 1.50 kilograms. The velocity is going to stay constant, and it's going to keep spinning at 3.00 meters per second. And we know that the string has a length of 0.75 meters. Now, it says the string has a length of 0.75 meters, and if we look at our picture, that string is connecting to a central point and going to the outer edge, which means that is also equal to our radius. The string will tell us what the radius of our circle is. And then from there, we're kind of left to our own devices. We don't really have a lot of other information, but we can make at least a couple of things that we can solve for. So first, we have velocity and we have radius, which means we have enough information to solve for our acceleration if we need it, because acceleration equals v squared over r. We also could try to plug in to find our period, but let's hold off on that. We may not need it if we're caring about forces, because the question is asking for what is the force of tension at the top, bottom, and sides. That's our unknown. We're looking for the force of tension. If we're involving a force, that is our cue. Okay, well, we're going to probably need acceleration in order to do something related to the forces. So let's go ahead and just get that acceleration just so we have it if we need it / when we need it later. It'll be 3 squared over 0.75. If you plug that in, I think I know what it is, but don't want to be incorrect. Over 0.75. Yep, we get 12. So that's 12 meters per second squared is our acceleration, which is pretty fast. That's a pretty fast speed. Or pretty fast acceleration, but it's also a small circle. It's a small object also, so we're okay with that. That's a reasonable number to get there. We also know that if that is the force that's acting on it, that's the force directing inwards, that's the acceleration that's happening. At every one of these positions, the sum of the forces must be equal to the mass times its acceleration. And if the acceleration is 12, well, then we know that our mass is 1.5 times 12. We get 18, I think. I'm going to plug it in just in case. 1.5 times 12, 18. 18 newtons. Again, remember this was the sum of the forces. Up here in this problem, it was the only force, so it just became equal to it. But here, when we're in the vertical direction, it may not be the only force. And in fact, it usually won't be the only force acting in that direction. So we have to kind of consider it just as sum of the forces, not as this is already going to be set equal to something. So these two values are useful. Let's go ahead and just let's pick one of the points. So I'm going to start with the bucket is hanging down. So I have my bucket. My bucket is going to be at the bottom position. First thing, I'm going to have the force of tension. Instead of the normal force, because it won't have the normal force because it's being swung in a circle, so it's off the ground, force of tension is the thing that's pulling it upwards, that's acting in that direction. We would also expect gravity to be acting downward. And when it's at the bottom, in order for it to swing, in order for it to have an acceleration, the sum of the forces has to be pointing inward. It has to be pointing towards the middle of the circle. We have to have a centripetal acceleration. So our total force, sum of our forces here, must be equal to 18 newtons. So this is our total force. Combined goes in that direction. We can go ahead and set it up then. Sum of our forces is equal to 18 newtons, which is Ft plus Fg. Now, we don't know force of tension. That's what we're looking for at this point, but we can find gravity. So force of gravity, just as a reminder, is mg, the mass times gravity. So in this case, that would be 1.5 times 9.8. This also seems like it's probably going to be a good value to have. So 1.5 times 9.8. We get 14.7, and that would be newtons, because that's our mass gravity. It's our force of gravity. So now we can just kind of rearrange this. Force of tension is equal to 18 newtons. Gravity is pointing downwards in this case, so it's going to be minus 14.7 newtons. It would have been minus over here, which means to rearrange it, we would have to do plus. Let me write that out so it's not as vague. So we would get 18 equals Ft minus 14.7 or plus negative 14.7. Then we'd add 14.7 to each side, and that would give us this over here. So 18 plus 14.7, our force of tension in the vertical direction is going to equal 32.7 newtons. Okay, simple enough. Our next position to think of, let's go ahead and do if it's from the top. So I'm going to go ahead and draw, I'm going to make a smaller square this time. We're going to have our string going this direction, which means our force of tension is going this direction. But also this time, instead of that voice crack, let me get a drink of water before I continue. I don't know if we can handle more voice cracks like that. All right. So since it's pointing downwards and since it's up in the air, gravity is actually also going to be going this direction. And we know, just like last time, our centripetal acceleration, our total force, therefore, has to point towards the middle, which at the top is going to point that direction. And that has to be equal to 18. Just like the last time, only instead of it pointing up when it's at the bottom, it has to point down towards the center when it's at the top. So we would get the same setup as before. Sum of the forces is equal to 18. This time it's downwards, though, so I'll actually say it's negative 18 equals Ft plus Fg. We can use the same Fg as last time because it's going to be the same value. So that'll be equal to Ft plus negative 14.7. But this time, our total force value is also negative, which means we will get Ft equals negative 18 plus 14.7, which actually is going to give us a smaller number. That's actually going to give us 3.3 newtons, which makes sense. The string doesn't have to provide nearly as much work when it gets to the top of the bucket swing because gravity is going to start pulling it around, and we kind of at the bottom have to be fighting against gravity to pull it back up on the circle. So this value here is a lot smaller than this value right here. Now you may be thinking, well, maybe we can make a guess about what's going to happen on the side, but at the very least you should hopefully realize it's going to be between these two numbers. So let's go ahead and think about at the side. Let's go ahead and do this, and let's go ahead and do this. Okay, our force of tension is pointing in there, but here's where we have some weirdness happening because if I scoot this down a little bit, oh, hold on a second. I think someone's at the door. Nope, looks like it wasn't. Okay, we're good. Okay, so force of tension is going to point inward. I think I talked about that. Okay, we'll come down here is going to be the force of gravity. Now this is where things get a little bit weird because now we know our total force has to point towards the middle here. And if it's going to have to point towards the middle, gravity is not really going to be doing anything. It's not even in the same X and Y axis as those two, the other pieces that we're looking at here, which means the force of tension has to be the only thing that's really going to be at play here. I'm having a little bit of a moment where I'm a little concerned about something. Let me check my work to make sure I don't steer you guys the wrong way. Okay, no. I got a little paranoid. I didn't want to have to mess up this whole video, but my logic is correct. My wording is correct. It will not come back to bite us later after I have checked my work. the force of tension is going this direction. Since the force of gravity is perpendicular to it, it's not affecting it. There's no component that is going to affect the total forces. Again, we could say that this was the total force pointing towards the middle would have to be the force of tension. Yes, gravity is going to make it harder to be swinging, but at that exact moment when it's on the side, all that matters is you're pulling inwards with the centripetal force. You're trying to pull it up towards the top as it's already got its speed that it's going. So because it's at a constant speed, gravity is not affecting it. We actually don't have to care about gravity affecting it at all. The only thing that's pointing towards the direction of the force that we care about, the horizontal direction, is the string. So some of our forces in our, to be a little more clear this time, x direction is equal to the centripetal force. So I'm going to label that as FC, my force centripetal, which in this case was equal to the value we found up here, which is 18 newtons. And if the only force is there, some of the force in the x direction is equal to the centripetal force, which is equal to the force of tension. That just means that the force of tension at that position is 18 newtons. So not only is it between it, it's literally just the centripetal force. The tension, the rope there is providing all of it. Gravity isn't trying to hinder that force going that direction in any way. Gravity is not making it easier. Gravity is not making it harder. Gravity is just there. It's not affecting the acceleration that needs to be pointing in that direction. Okay, sorry about that paranoia, but again, really didn't want to lead you the wrong way into a 20-minute video. That's what I've got for today, though. If you have any questions, please shoot me an email. Otherwise, this is Mr. Diamond signing off. Have a great rest of your day, everybody.